In this lesson, we are going to discuss mechanical energy. At the end of this video lesson, you should be able to define kinetic, potential, and mechanical energy, and describe the mechanical energy of an object at different times. Let us start this lesson by looking at how this man does work by pushing a cart. For him to do work, he must exert a force on the cart. Second, the cart should have a change in displacement. And lastly, the force exerted on the cart must be in the same direction with the motion of the cart. In this context, work does not mean one's career or employment. It does not also mean a product of one's effort. Rather, work in physics is defined as the product of the magnitude of the displacement multiplied by the component of the force parallel to displacement. A force exerted on an object, even if it is not parallel to the displacement of the object, can still be used as long as we get the component of that force using the trigonometric function cosine. When the force is parallel to the object, it can be simply written as work is equal to force times displacement. Its unit will be kilograms meters squared per second squared, or Newton meter or joules. For a certain system to exert force and cause a displacement on an object, the system must have a capacity to do work, or what we call energy. Energy is the capacity of a physical system to perform work. Its unit is the same with the unit for work. Energy changes from one form to another. For this man to perform physical work, the energy stored in his body in the form of chemical energy, which is obtained from the food that he eats, is changed to mechanical energy and heat energy. Mechanical energy is the sum of the potential and kinetic energies of a system. It is the energy which is based on the object's position and motion. Let us discuss thoroughly the components of mechanical energy. First, let us discuss kinetic energy. It is the energy possessed by bodies in motion like the car as it moved in the previous animation. Since kinetic energy is the energy in motion, Newton's second law of motion is used to describe how the force exerted on an object's mass allows it to accelerate. If the net force is constant in the system, acceleration can be described as the final velocity squared minus initial velocity squared all over twice the displacement of the object. Substituting acceleration in Newton's second law of motion, we are going to have this expression. To see how the force exerted on an object allows work to happen, we can multiply both sides of the equation with the displacement. Thus, we have this formula. Expanding the ratio for the velocities, we are going to have the difference of half of the final velocity squared and half of the initial velocity squared. Lastly, distributing the mass of the object, we are going to have this equation. Since this equation describes work in terms of an object's mass and velocity, we note this difference as the difference in kinetic energy. This gives us the work energy theorem. This means that half of the product of an object's mass and the square of its velocity at a certain time is the object's kinetic energy at a certain time. This equation reveals that the kinetic energy of an object is directly proportional to the square of its speed. This means that if the speed of an object is doubled, its kinetic energy is increased by a factor of 4, which also means that it takes 4 times the work to double the speed. Similarly, it takes 4 times the work to stop an object moving twice as fast. The next component of mechanical energy is the potential energy. It is the stored energy of an object in an elevated position. In this lesson, we limit the concept of potential energy as the gravitational potential energy, or the energy which an object possesses at height h above some zero reference level. In this figure, the kettlebells have a certain weight which is equal to the mass times the pull of gravity. These people need to exert a force to lift which is also equal to the weight of the kettlebells. Since the force exerted by these people are upwards and the displacement of the kettlebells are upwards too, we can say that work is done. This can be found by multiplying the force needed to lift the weights by the distance the weights had to be moved. Using the force to lift equivalence, we have this equation. For the displacement, it is the height lifted against gravity that matters and not the actual distance moved. We now describe gravitational potential energy as the product of the object's mass, vertical position or height, and pull of gravity. Let us now look at the changes in energy as one does work. The hand does work to lift the ball up to the air. The x-axis represents the time reference of the ball's location, and the y-axis represents the height of the ball at a certain time. At time A, chemical energy from hand is transferred to the ball as the kinetic energy. This shows that kinetic energy is highest on the ground. At time B, both energies are present on the ball since the object is moving and that the object is at a certain height. At time C, the ball experiences a momentary stop because it is at its maximum height. Thus, kinetic energy is zero and the potential energy is at its maximum. At time D, the object is still moving at a certain height. Thus, just like in time B, both energies are present on the ball. Lastly, at time E, the kinetic energy is at its maximum and is eventually changed into internal energy and sound energy. Potential energy is zero since the ball is at height 0. Now, let us quantify the energies present on the ball from time C to time E. At time C, since only the potential energy is present, we compute it using the product of the ball's mass, the height that it has reached, and the pull of gravity. Assuming that the ball has a mass of 0.15 kilograms, we can substitute the following values into the equation. This means that the potential energy at time C is 10.30 kilograms meters squared per second squared or 10.30 joules. At time D, since both energies are present, we can quantify both energies present on the ball. At time D or at height 5 meters, the potential energy of the ball is 7.35 joules. Suppose the ball has a velocity of 6.27 meters per second at this time. Its kinetic energy is described by this equation. Thus, at time D, the ball has a kinetic energy of 2.95 joules. Lastly, at time E, no potential energy is present at the ball, but its kinetic energy is at its highest. If the ball has a velocity of 11.72 meters per second, its kinetic energy is 10.30 joules. Since mechanical energy is the sum of the potential and kinetic energies of a system, we can look at the mechanical energy of the ball at each selected time from the previous part. At time C, the ball has a total mechanical energy of 10.30 joules. The same goes with time D and time E. We can infer from this data that the mechanical energy of a system is constant at any time. Thus, mechanical energy is conserved in a system. The law of conservation of mechanical energy states that the sum of the kinetic and potential energy in a conservative system is constant and equal to the total mechanical energy of the system. It is denoted by the equation initial kinetic energy plus initial potential energy is equal to the final kinetic energy plus final potential energy. Replacing the components of mechanical energy with the formula studied, we are going to have this expanded equation. Take note that the initial and final time here does not always indicate time 0 and the actual final time of the object. It may also indicate two different times, the earlier time being the initial time and the latter time being the final time. To wrap up this lesson, let us review the following key points. Mechanical energy is the sum of the potential and kinetic energies of a system. Potential energy is the stored energy, and kinetic energy is the energy in motion. And lastly, the law of conservation of mechanical energy states that the mechanical energy is the same at different times. And that ends our discussion on mechanical energy.